So if you like this video, hit that like button. If you want to comment, please do so. If you want to share amongst friends, family, colleagues, then please feel free to share this video tutorial. And please make sure you hit that subscribe button so that you get the latest updates and videos. With that being said, let's get on with this OSPF tutorial presentation. Hi and welcome to this presentation of what is OSPF and how does it work. We'll try and do this presentation as quickly as possible for you. So what is OSPF? Well, it's Open Shortest Path First. It's a dynamic routing protocol and it's an open standard, which means it'll work with pretty much any router. So your Cisco, your Junipers, your Extremes, etc., etc. It's what we classify as an interior gateway protocol. That means it's been designed to be used within a single autonomous system. And it's a link state routing protocol based on the Descriptor routing algorithm. How does it work? Well, as per all routing protocols that are dynamic, the goal of OSPF is to learn routes. OSPF does this by learning about every other router and subnet within the entire network. So the end result is that every router should have the same information about the network as every other router. And the way the routers learn about this is by sending out LSAs or link state advertisements. So the LSAs contain all the information about the subnets, the routers, and other network information, and we'll go into that. Once all the LSAs have been flooded, OSPF keeps all this information in a link state database. This is also known as the LSDB. The goal being, or the end goal being, that each router has the same information in their LSDBs. Now, the above that I've just noted is a general idea from a high-level perspective of how OSPF operates. What we're going to do is we'll go in a little bit deeper now and look at how all of this functions. So let's take a look at the three main processes of OSPF. Well, the first is to become neighbours. So two connected routers running OSPF on the same link agree to form a neighbour relationship. They exchange database information. So the neighbour routers will swap their link state database information with each other, as we mentioned in the previous slide. And they'll choose the best routes, and each router will choose the best routes to add to its routing table, and that'll be based on the learned LSDB information once the LSDB information has been exchanged. So this is completed by running a calculation called SPF, which stands for Shortest Path First. And again, now let's go into diagrammatic depth to try and explain this a little bit further. So how do the routers become neighbours? So the first thing they must have is a router ID, and it must be unique. So each router must choose a router ID before a relationship can be formed. The router ID is a number that can be used to identify an individual router. The router ID itself is in the form of an IPv4 address, but can be set manually to whatever you would like it to be. So below we're going to list the methods that can be used to set a router ID, and there's only actually two. There's manually or there's dynamically auto. So the router decides for itself. Manually you set the router ID. And there is a process that the router has to go through, which is a logical process when the router wants to decide for itself. So the first thing the router will do is it will check if it's been manually set. If it has, it doesn't have to decide for itself. And if it has been manually set, then that's the router's ID. You've set it manually. If it's not manually set, then the router will choose the highest up loopback IP address. And if there's no loopback interfaces available on the router, it will choose the highest up non-loopback IP address. So with the above process, the router will actually choose the highest IP address on the router as the router ID. So the easiest way to explain the above process is for us to have a look at two routers forming a neighbour relationship. So let's go ahead and do that now. So here we have the two routers. don't be too concerned about where it says down, down. R1 and R2 are not physically down. This is so that we can show you, or the down, down is a representation of the current neighbourship relation, so that we can show you from the very beginning. So once we've got OSPF configured and the RIDs are in place, the routers are going to contact potential neighbours and send a hello message. So the hello message that router 1 is going to send to router 2 is going to contain important information like its router ID and any neighbours already established. So the message also lets router 2 know that it's still alive. It's saying, hello, I'm still here. So when router 2 receives the hello message, it runs some checks. Now, OSPF has some very strict requirements that need to be conformed to for it to form a neighbour relationship. And these are those requirements. So the area ID must be the same. The subnet must be the same. The hello and dead timers, or the interval timers, must be the same. The dead timer is basically a specified time that you can manually set, that router 2 will look for a hello packet from router 1, and if it doesn't see it within that time limit, it states router 1 is down, or at least the link to router 1 is down. It can't see it anymore. The hello timer is 10 seconds, so the dead timer will obviously have to be above that hello timer. Okay, so the authentication must be the same if we're utilizing passwords for this neighborship relationship to occur. Okay, and the stub area flag must match, and the routers also require unique router IDs. Once all the checks have been made and they're okay, router 2 can move to an init state. Router 2 then sends its own hello message back to router 1, and it'll include its own router ID, but now it will also list router 1's router ID, or RID, as a neighbour. So its own RIDler is 5555 and the neighbours is 4444. This means that when router 1 receives this message, it will see itself as a known neighbour. This will allow router 1 to move to what is known as a two-way state. Router 1 will then send another hello message which will list router 2 as a known neighbour, and it will send this to router 2. When router 2 sees this, it will also allow itself to enter a two-way state, as we see. So the end result of the information exchange is that we now have two neighbouring routers. Now that we have the neighbouring in place, we need to have a quick look at designated routers and backup designated routers. So what we're looking at here at the moment with these two routers is what is known as a point-to-point connection. So that's the example that we're showing. To understand the designated router and backup designated router requirements, we have to have a quick look at a broadcast network. So we're going to go ahead and do that now. So in this broadcast network, we can see that we've got 6 routers all connected on the same segment to this switch in the middle. Now, what we're going to do is we're going to currently look at it from the perspective that we don't have a DR or BDR and that all routers become neighbours with each other. And we'll see what the problem is within a broadcast network. So let's say that we have a link that fails. Let's say this link here fails. This router would have to let all the other routers know that this link has gone down. So it will send it down to the switch and it'll forward that to all its neighbours. Okay, so all the neighbours now know that this link is down. So the problem is that each of these neighbours in turn would then also have to tell the neighbours that that link is down. So they would have to send a packet as well. So before we know it, things are going to get a little bit out of control with regards to this, and we're going to have packets of flying around this network that we don't need to be going around the network. So instead of that happening, what happens is a designated router and a backup designated router are elected. Now, the election of a designated router and backup designated router, that is based on the highest OSPF priority. By default, the priority is set to 1, but it's important that we note that we can manually change this to influence which router we want as a DR or BDR. And we'll see why we might want to do that in later lessons. But it's also explained slightly in the next statement that if the election is tied, the result is based on the highest router ID. And given that by default the priority is set to 1 and we haven't set any priority on any of these systems, then they're all going to be 1, 1, 1, 1, 1, 1. So let's just say that this has the highest RID. So this router becomes the designated router. This router has the second, so it becomes the backup designated router. Now what will happen if that link goes down? Well, okay. When they're on the same network segment, the OSPF routers will only become neighbours with DRs and BDRs. The others will remain in a two-way state that we previously examined. So that means that all routers will ignore updates unless they come from the DR. This means that if the link went down now, these routers here would ignore the updates from this router. What will then happen is the DR will have also received this update, and it will then flood the network with that update. And at that point, these routers will then pay attention to that update. So that's how this works, and the neighbour relationship works within a broadcast network. So what we're going to do is we're going to revert to the original diagram now of the point-to-point and continue with how the OSPF operates. Okay, so once the exchange process has begun, both routers enter the exstart state, as can be seen here. Router 1 has entered the exstart, and router 2 has entered the exstart. This is the point where the routers actually select a slave and master, and that again is based on the router ID. So the highest router ID will become the master. The master controls the sequence numbers and starts the exchange process. At that point, we move into what's known as the exchange state. Now, in this example, I'm going to include some IP addresses so that we can see what happens with the link state updates. So as we see, router 2 knows about the 70 network because it's connected to it, and router 1 knows about the 50, and they share the 60 subnet. So both routers will send each other a list of their LSAs. They're also known as database descriptors or database description. At this point, we move into a loading state, as can be seen on router 1 and router 2. So each router takes a look at the database descriptor and requests any information it doesn't already have. And the reason it does that is it stops other routers sending information that it doesn't actually need. So it prevents unwanted CPU and RAM usage on the actual routers themselves, because there's no point having information that it's already got. So it's basically saying, router 1 is basically saying to router 2 here, hey, send me over that LSA for 192.168.70. So it requests router 2 to send over that network information. So router 1 actually sends a request to router 2 for the information. And this is called a link state request. So we have the database descriptor followed by the link state request that router 1 sends to router 2. Router 2 responds by sending the requested information in a link state update, and it sends that back to router 1. So we have the database descriptor followed by the link state request from router 1 to router 2, followed by the link state update from router 2 to router 1. Router 1 sends a link state acknowledgement back to router 2. This same exact process occurs with router 2 as it needs the information from router 1 for this .50 network, the 192.168.50.0. So that exact same process of viewing the database descriptor, examining it, sending a link state request, a link state update is responded with, and by router 1 and router 2 responds to that with a link state acknowledgement. Once that process has been completed, both routers can now enter the full neighbour state. Again, as I've stated down here, it's important to note that what we're looking at here is a point-to-point network. On a broadcast network, they will only form relationship with DRs and BDRs. So how does OSPF know what is the best route to insert into its database? Well, that is based on cost, and it has to perform a calculation to work out that cost. How does it perform that calculation? Well, the cost calculation is a value associated with a link, and it's based on the bandwidth of that interface. Then the calculation is the reference bandwidth, which is set on the router itself, and it's 100,000 kilobits per second by default, and that is divided by the interface bandwidth. So, as I've stated here, don't worry too much about the actual calculation at the moment. Just remember the cost that I'm about to give you now. So we have the interface, we have the default bandwidth, and we have the actual cost. So we'll have a serial interface at 1.544 kilobits per second. That's a cost of 64. We have Ethernet, 10,000 kilobits per second, cost of 10. And then we have fast Ethernet and above 100,000 kilobits per second at a cost of 1. Now you'll probably be thinking, well, hold on a minute, we've got 1 gig interfaces now, we've got 10 gig interfaces and above, but they're all only going to be a cost of 1. So how does that make sense? Well, you'd be correct with that train of thought and that way of thinking. But the way you can change this is to change the reference value in the calculation. You can do that manually. So you can configure this value on the router itself. So now what we're going to do is we're going to go through a cost example to see how it all works. So here we have a 5 router layout. At router 3's end, we have a prefix of 10.0.0.0, and at router 1's end, we have a prefix of 192.168.50.0. So in the example below, or in this example, router 1 wants to add router 3's known prefix of 10.0.0.0 to its routing database, or its routing table. So as we can see from the diagram, it's actually got 3 options. So option 1, it can go this way through router 2 to router 3. The second option is it can go router 4 to router 3. Or it can go via router 5 to router 3. Those are the 3 options. So it needs to make a decision as to what is the best cost, and it will do a calculation to work out that cost, as we've already mentioned. So let's say we work at the first option, which is through router 4. So the link between router 1 and router 4 is serial, and it's 1544 kilobits per second. So that's a cost of 64. The second link is also a serial from router 4 to router 3, and that's a cost of 64. The third route, or the third link, is a 10 megabit route. So that's a cost of 10, which equals a total cost of 138. Now let's take a look at the second option, which will be through router 2 to router 3. So we have a 10 megabit link between router 1 and router 2, a 10 megabit link between router 2 and router 3, and we know that it's 10 megabit from router 3. So we have a cost of router 1 to router 2 of 10, router 2 to router 3, 10, and router 3 to the network, 10, which gives us a total overall cost of 30. And now let's take a look at the third option, which is through router 5. Between router 1 and router 5, we have a 100 megabit link. Between router 5 and router 3, we have a 100 megabit link, and from router 3 to the network, we have a 10 megabit link. So that gives us from router 1 to router 5 a cost of 1, from router 5 to router 3 a cost of 1, and from router 3 to the network a cost of 10, which gives us an overall cost of 12. So as we can see from this description and looking at these routes, router 5 direction, the 100 megabit direction with a cost of 12, is the lowest cost, and therefore that's the route that will be added to router 1's routing table. So any data that comes through from 192.168.50.0 at router 1 that is destined for router 3's 10.0.0.0 network will follow the path of router 1 to router 5, router 5 to router 3, and router 3 to the network. So guys, for this video, that's enough information, I think, for you to actually understand how OSPF itself works from a high-level perspective. There's an awful lot more to OSPF than what we've covered here, but I wanted to give you the high-level overview first. So, if you like this video tutorial, hit the like button and don't forget to subscribe, because then you'll get all the notifications of the next OSPF tutorials and, more importantly, the configuration work that we're going to do so that you can actually see it in action. So it's great to see you guys here. Thanks for watching, and we hope to see you soon.